Yeah, am I audible? Uh,
Yes, go ahead.
yeah, okay. So thank you everyone for inviting me into this panel, and also thanks to all the speakers prior to me who have basically have described the problems in a very thorough and a detailed manner. So what I am going to talk about is I'm going to talk about regarding the hardware aspects of the post-quantum cryptography. So as it was pointed out, that PQC algorithms are going to be an important aspect in the quantum cryptography research, and the topic of hardware security is also going to be applicable in case of post-quantum algorithms also. So the topic of hardware security, we have typically two parts. First part is the implementation of this algorithm. So whatever PQC algorithms, whether it's lattice-based or code-based, how to implement them efficiently on a hardware architecture. And of course, preventing the side channel fault attack or the hardware Trojan-based attacks on these cryptographic algorithms. So, as it is already known, quantum computers are going to be arrive soon, maybe not in 20 years or 30 years, sometimes it will arrive. And at that time, the RSA relative curves and all the security protocols based on those algorithms are going to be vulnerable. So, NIST has created this competition. Sorry for these slides, there typically has some error have occurred. But typically there are now round four results are there. In the round four results, we have crystal Kyber and crystal dilithium chosen as standard for the key encapsulation and digital signature algorithm. Alternatively, we also have BIKE, HQC, Psych, and classic MACLIS as the key candidate or the candidate for key establishment algorithms, and Falcon and Sphinx Plus as the candidate for the algorithms for digital signature. Now, please note that Psych recently, after the round four was published, has got broken, and therefore it is very important that we do not really focus on one particular algorithms. Rather, we develop a generic architectures or generic hardware framework which can support multiple different algorithms, such that if one algorithm gets broken or if the specification of the algorithm changes, we can very quickly switch to the new algorithms or new specification. Now TLS 1.2, 1.3, we already have an OpenSSL benchmark or libraries which integrate OpenSSL NTRU, which is one of the round three candidate for the post-quantum algorithms. Now, when we talk about hardware implementation, there are two ways we can implement any hardware architecture. So one of the way is to you create a hardware peripheral. For this example, we are considering Psych P434 architecture, and you create an AXI interface to communicate between the processor ARM based and the corresponding hardware accelerator. Now this scheme works, but the issue with this kind of scheme is that the time to transfer the post quantum data has very large dimension, and the time to transfer the data from the software processor framework to the hardware is going to be much larger than the actual operation that is happening in the hardware. So as you can see in this example, we are spending around 5,000 cycles to transfer data, around 2,000 cycles to read the data back, but a simple multiplication which this architecture is doing, taking only 154 cycles. So for this kind of framework, we suggest that you kind of use an internal memory. In FPGA framework, we can use block RAMs to create this kind of architecture, and we can resolve this problem. So when you have this kind of memory, rather than passing the data, you can just pass the address of the data stored in this memory to do the corresponding operations. Now, this works, but the issue again is the overhead of this corresponding architecture. So in that regard, we can take advantage of the RISC-V phenomenon that has also recently occurred in the domain of computer architecture and organization. And in RISC-V framework, we have the full control of the open instruction set architectures, and you can basically integrate the corresponding algorithms or corresponding frame architectures or hardware accelerators directly to the register bank of the RISC-V. So here you do not have any communication for the ASIC and communication for the AXI protocol, and therefore it is much faster than the ARM implementation or some fixed ISC implementation, where you do not do not have the ability to modify the corresponding hardware or corresponding ISC. So once we fix this implementation framework, like whether you are doing ARM accelerator or RISC-V accelerator, and depending upon that, we create the basic framework of this architecture or this hardware accelerators. The other thing would be that how you can make sure that a single architecture can support multiple PQC algorithms. So taking advantage of the entity-based multiplier properties, we actually have developed a single architecture which uses a property called entity-friendly prime and entity prime lift, which can support all the listed lattice-based cryptographic algorithm. So in this case, you will have single entity multiplier, which can support New Hope, Kyber, which all were either in round 1, round 2, or round 3, the candidate of NIST competition. And therefore, even if, for example, tomorrow the crystal Kyber gets broken and the NIST recommends to integrate Saber instead of crystal Kyber, we can do that easily in the hardware framework without doing much modification. Compared to that, if you have a fixed architecture for crystal Kyber and suppose crystal Kyber exhibits some vulnerabilities in near future, then you have to completely replace the corresponding hardware architecture. Now, ASIC design is not cheap. So if you're creating an ASIC design or even an FPGA implementation, replacing that is not cheap. And therefore, developing generic architecture supporting multiple PQC algorithms is very important, as we never know when there could be a classical computing or even quantum computing algorithms that can break this system. One case study would be Psych, which has survived near 20 years of cryptanalysis, but recently got broken by a classical computing framework within 7 hours. So that is the reason, as a hardware engineer, I recommend to develop generic architecture for PQC algorithms. And of course, that also solve the problem of, this is a strategy that we used, and this is the corresponding entity architectures that we have developed. So this single entity architecture can support multiple, all the listed lattice-based cryptographic algorithms. So another important aspect of any hardware implementation is side channel security. So once we implement the computational intensive operations of post-quantum cryptographic algorithms on FPGA or ASIC, and we develop the corresponding hardware software co-design, we need to do the side channel analysis, and we can use the state-of-the-art side channel evaluation and leakage detection method to detect whether there's a leakage or not. For example, in this case, we are actually exhibiting the value of student t-test or TVLA, test vector leakage assessment, which are the de facto standard nowadays to detect whether there's a leakage or not. Without going into much details, if we can see a value above or below plus minus 4.5, we see there is a leakage. And when you are developing a secure, completely secure PQC algorithm, you need to focus on every aspect of that corresponding algorithm. Now, standard PQC algorithm, lattice PQC algorithm will have the hash function, which can be implemented by KCHAC, or we need to have the sampler, need to have the operation of mask converter like Boolean to arithmetic or arithmetic to Boolean conversion. And as you can see, that without the masked countermeasure, there is a very high amount of leakage which can reduce when we replace the unmasked design with a masked implementation. So this will also allow us, like once we create this kind of generic frameworks and generic secure framework, this will also allow us to create a much more dependable hybrid system where we can support pre-quantum algorithms relative cut and the post-quantum algorithms, for example, say code or lattice together, because there will be a time where there will be switching over will happening, but at that time we would require to support both class of public key algorithm, like both pre-quantum and post-quantum public key algorithms. Now, generic architecture or generic hardware, generic secure hardware is going to be the solution to solve that problem. And also, there is a short signature scheme, the call for short signature scheme recently announced by NIST. So in that case, there will be more new algorithms will be submitted, the NIST call proposal, and which will have very short signature size. And that means that the field of PQC algorithms, cryptanalysis, and also the corresponding hardware design, side channel attack, is going to remain very, very interesting in the upcoming years. So in that note, I will conclude my presentation. Thanks everyone for their patience.